All right, in this lesson, we're going to look into how to deal with multiple vectors to get kind of a final vector from that. Okay, and I'll give you an example. I'll give you like a motivation for this. So our starting thing is we're at this origin, the red dot, and somebody goes off and follows a path. So they follow the red line, and then they follow the blue line, and then they follow the green line. And that's a lot of following. That's a lot of lines, a lot of distance. We don't want to do that right now. We want to actually just meet them at the end. So we want to know in what or how far and in what direction do we need to go in order to just meet them at the end of this without having to go through that long path. So that's what we're going to try to find. The way that we do this is we take all the vectors that the person walked along, and we break them into what we call x and y components. That's just how much did they move in the x and how much did they move in the y for each of these vectors. So for the red one, how far did they move in the x direction? How far did they move in the y direction? So I'm going to show you graphically how this works and how this will help us find out what the purple line is. And then I'm going to take you through a more mathematical approach to the whole thing that'll let you handle any type of situation, any type of problem that involves multiple vectors. So I'll draw this out. So let's say we're starting at the origin. I'm just going to draw the horizontal stuff so that we can see it. So I'm going to start here. I'm going to go over to about here. Oh, that's too far. It's close enough. So we're going over to about here, which is where the red line ends. So I'm just kind of like following this down, right? To where this projects to, or how far in the x direction that this person travels on that red line. And then I'm going to do the blue line, and that's not so long. It only goes to about there. And then we have a green line, which goes back. So we're starting over here, and we go all the way back to here and to that point. Okay. The result of this that I want is to be able to just go from the beginning to the end. And this is really easy to see if I just focus on the x direction, right? Like I only need to move a little bit in the negative x direction. I've labeled to the right as my positive x, so that means to the left is negative x. And down is negative y if up is positive y. So I did that in the x. I'm going to do the same thing in the y direction. So I'm going to start with the red. And we go up to about there. And then we do blue, and with the blue we end up coming down to about there. And then we go down a little bit further. So we go to this location. Okay. And now the purple is going to take me from the beginning to the end. Okay. So this is the idea. I only care about that purple line ultimately. Now how this helps us, just so that you can kind of see how we can get these purple lines, is if I know the size of all the other vectors in the x direction and in the y direction, I can get the purple result pretty easily. So this red line, for instance, is 2, 4, 5.5, I believe. It's about 5.5. The blue one is about 1, and the green one is about negative 8.5. And so what I can do is I can say, well, to get the result, so I'll call this vector r. So to get the result in the x direction, because that's what this is, result in the x, I'm just going to do 5.5 plus 1 minus 8.5, and that should get me negative 2.5. Nope, negative 2. Okay, so that gets me negative 2, which we can see graphically, right? Like I can see that over there. How do I get that? I add up all the vector components that are in the x direction, and what's left over is my result. Or what I get when I add it all up, that's my result. And notice that it says negative because that, for vectors, we care about the size, but we also care about the direction, and that's pointing in the negative direction. I can do the same thing with the vertical stuff. So this looks like it's about 4.5, and the blue is about negative, we'll just say it's negative 6.5. It's pretty close. And the green one looks like it's about negative 2. So this is not exactly right, but it hopefully gets at the idea. And so then I can say, well, what's my result in the y? So my result in the y is just 4.5 plus negative 6.5 plus negative 2. So I'm putting the pluses in because technically what I'm doing is I'm just adding everything, but sometimes things are negative, and that's fine. So I end up with 4, negative 4. Okay. And again, because this is a vector, I have a size of 4, so my arrow is about 4 long, and my direction is negative, so I have the negative sign there. So this is what I end up getting. Now, how does that help me if I just want to go in a straight line? Like, I just want to know the total distance between the red point and the end point here, which I'll make green, make that a green dot. I want to know that total distance, and I want to know the direction. Well, one way to say it is go 2 left and 4 down, or like 2 west and 4 south. That's fine. But I can also use some of the math stuff that we already learned, which is I can say, I've got this vector that goes 2 over, and I've got another vector that goes 4 down. And then what I ought to be able to do is get a resultant vector for that. So I can go and find out what is the total. So this is Rx, this is Ry, and this is R. And then there's also going to be an angle here, and I'm going to use a different color for the angle. So I'm going to make this the angle theta. So how do I find the R? So once I get these sides, this is kind of the magic part. Like once I get these sides, I can just go back and use a triangle to get R. This is stuff we've already learned. So I can say R is equal to the square root of Rx squared plus Ry squared, which in this case is negative, I guess that's 2. Negative 2 squared. When you square a negative number, I don't know if you know this, but you get a positive. And then negative 4 squared. And so this just becomes the square root of, that's 4 plus 16, square root of 20, which is about 4.5. I'm not going to be too particular about this because I'm not doing the math. And if I look over here at my actual line, right? This line right here, that's about 1, 2, 3. It's close to 4. There might be something that I've done a little bit wrong in here at some point, but that seems reasonable. It's hard to tell because it's on a diagonal, but it's about 4.5. Okay, so I go over here and I can try to find the angle. So I knew the 2 sides here. This is the adjacent side, and this is the opposite side because it's opposite to the angle, and this is the nice right angle here. The hypotenuse I'm not going to use to find the angle just because it's a value I found, so I could have screwed that up. The fewer things I screw up, the better. So I'm going to do tan inverse of opposite over adjacent equals the angle. And then I can plug that in, and I can get tan inverse of, and here the negative signs aren't really going to matter. We'll worry about that later. So normally when we're doing this, at least at first, we won't worry too much about that because I've kind of just made a triangle over here. So I'm just going to use the sizes of these for now. So my opposite side was 4. My adjacent side was 2. And now I have the tan inverse of 2, which I need to actually see what that is. Arctan of 2 is, I need that in degrees. Okay, that's about 63 degrees, 63.4 degrees. And that kind of makes sense. It looks like it's more than 45 degrees, so 45 is like halfway between the x and y axis, and that's 63.4. Okay, so not too bad. That's what we have, right? So our process is going to be find out how much every vector that leads to the result that I want, how much of those vectors are in the x direction, add all that up, how much are in the y direction, add it up, and then make a new triangle for my result using the total x and the total y, and then use Pythagorean theorem and tan inverse. So I'm going to write out this as a process here. So process. Step 1, well, draw vectors, right? If you don't have the vectors yet, draw them. Step 2, find x, y components of each vector. Okay, so this is the part I'm going to start because this is what we're going to actually focus on more next. I drew it up here. It's pretty easy to just draw them, but you can get a lot more precise answers and honestly a lot faster by focusing on the math part. So that's the part we're going to really focus on next. 3, add all x's, add all y's. So we're going to add all the x's together. We're going to add all the y's together. That's what we did over here to get the rx and then the ry. And then our fourth thing is draw resultant triangle. Right, so we're drawing the resultant triangle, which is this thing right up here. And then we'll use that to find size using Pythagorean and find angle using tan inverse of opposite over adjacent equals the angle. Okay, so this is our process. This I think we can do. I already showed you how to do that in a previous one, and it's just the same process for every time you do this. You would just do the same thing. You're going to have one final x total, one final y total. You just square them, add them, get the number, and do your tan inverse. Okay, it's a little bit more complicated than that sometimes, but that's really what it is. Adding things, I think you can probably add a couple of numbers together without too much trouble, so I'm not too worried about that part. And that leaves this part right here. So find the x and y components of each vector. So let's do this. Let's try something here. So I'm putting this on an axis, but my axis may not be perfect, as you can see by that slant there. And I'm not too worried about it because I'm not going to use the graph per se to help me with this. So let's do something like this. So I'm going to start like this. So this will be R1, and then I'm going to have an R2, and I'm just going to kind of make up some numbers here. Let's do this. Okay, so that's R2, and so my resultant vector is going to look something like that, right? That's what I'm looking for. That's my big R there. Okay, I'm going to give you numbers for these vectors. So again, it's not going to be exactly what it looks like on the graph. That's just to give us some idea of what we're looking at. So this will be theta 1, and then this will be theta 2. Okay, so we'll have both of these angles from the x-axis, but one's above it, one's below it. Okay, so let's say that R1 is 4 miles, and theta 1 is 70 degrees. We also have R2, which is equal to 6 miles, and theta 2, which is equal to negative 25 degrees. Okay, so what I've done here is given us distances and angles for each of these things. I'm not going to worry about that negative sign really right now. That's just to let us know that it's below the axis. So what I'm going to do is I'm going to split this up into x and y components. So this one I'm going to split. Well, I want to ultimately draw, like, find out what my x's are so I can add them up. Okay. The way that we do this is we don't use this picture anymore. This is just to show us what we think is going on. Now what I'm going to do is I'm going to make basically a new picture for each of my vectors. So R1, which is doing something like this. So I've got R1, that's equal to 4, and this is 70 degrees. And what I'm going to do is I'm going to take this and I'm going to split it into an x component. So R1x and a y component. So R1y. And I want to find out how big these are. Okay? So to find out how big they are, I'm going to use the idea of sines and cosines and that sort of thing. So this is the adjacent side. This is the opposite side. And this, of course, is the hypotenuse. And I know the hypotenuse and I know the angle. So I want to use a trig function that has to do with hypotenuse. If I'm looking for the opposite side, that's going to be sine. So I can go sine of theta equals theta 1 equals opposite over hypotenuse. And I'm just going to solve for the opposite side. So that means multiply everything by the hypotenuse. Okay? So that ends up giving me R1 times the sine of the angle equals R1 in the y direction. And I can plug in the numbers and I can find out what that is. I can do a similar thing for, well, I'm trying to think of if I actually want to do this. I guess we can. So normally I'm number averse. I don't really like numbers. I like to deal with symbols instead. But this is 4 times the sine of 70, which is 3.76. Okay. And then we're going to do something similar for the adjacent side. So for the adjacent side, I'm going to use cosine theta 1 equals the adjacent times the hypotenuse. And I'm going to multiply both sides by the hypotenuse to get that the adjacent side, which is R1x, equals R1 cosine of the angle. And that means that I have 4 times the cosine of 70 degrees, which is 1.37. Now you might be looking at this and saying, well, something is a little weird. Shouldn't these two components add up to be 4? No, they're not on the same axis as each other. So you need to go a little bit, you need to travel a greater distance if you're going just in x and y than if you just went in a straight line. Okay, I have my x and y components now for this first picture. Now I'm going to go and do another one for the second one image. So we're going to have, I'm just going to kind of go fast here because my picture isn't that important, but I'm going to draw it like this, like so. And this is R2, and I'm going to have R2 in the x. I'm going to have R2 in the y, and we're going to have an angle in there, which I'll call theta 2. And I'm just redrawing this picture, right? So I've got my vector, and I'm splitting into how far to the right did we go and how far down did we go. And to find these things, I'm still going to kind of label things using, this is adjacent, this is opposite, and this is the hypotenuse because it's the longest side. The adjacent side's touching the angle, the opposite side is opposite to it. Okay, so I'm going to find how much in the x we are, how much in the y we are. So let's start with the this one. So if I'm looking for R2 in the y, I'm going to use my sine. So I'm kind of jumping ahead here a little bit because it's the opposite side. So I'm doing sine theta 2 equals opposite over the hypotenuse. I'm going to multiply both sides by the hypotenuse, and I get R2y equals R2 times the sine of theta 2, which we were told that this was 6 and 25. So I have 6 sine of 25. And here's where you can take a couple of different approaches. I am going to encourage you to take the approach, at least initially, of look at the direction of that arrow. That arrow is down. So that's in my negative direction. So I'm just going to put a negative sign there. Okay? You are the one looking at the arrows. You're the one who can see if they're in the positive direction or the negative direction. So that's in the negative direction. So I'm plugging that in. I get 6 times the sine of 25 degrees. And that's going to be negative 2.54 as my result. Going to do a similar thing with cosine. That's adjacent over hypotenuse, which means that I'm going to get R2 in the x, which is the adjacent side, times the hypotenuse, equals the hypotenuse, times the cosine of the angle. And that gets me, now this is in the positive direction, right, because it's pointing to the right. So that's 6 times the cosine of 25 degrees. And that is 5.44. Okay, so those are our numbers. Now that I've got these, what I'm doing is I'm just going to add up all the x's and I'm going to add up all the y's. So my resultant vector, so if I look at this here, my resultant vector in the x is just going to be r1 in the x plus r2 in the x, which equals 1.37 plus 5.44. So r in the x is equal to, if I can do a little bit of math here, I think that's just 6.81, okay? And then I can do a similar thing in the y direction. So we have r1 in the y plus r2 in the y, and that's 3.76 plus 2.54. So that means that we end up getting, is that, and then I think 6.30, I think is what we get. Okay, so that's telling us what the total is in the x and in the y. So we get a little bit more x than we do y, but it's pretty close. Okay, so now that I've got this, if I go back to my checklist over here, so we drew the vectors, check. We found the x and y components of each vector. So this is the longest part, right? Like that's this part right here. So this is step 1, kind of like drawing it out. This is step 2, finding those components of every vector. And then this is step 3, where we added all the x and y's together. That's easy. And then step 4 is draw the new triangle. So let's draw a new triangle. So that's step 4. So I'm drawing my new triangle, and my new triangle just goes over a bunch. So that's 6.81, and it goes up almost as much, which is 6.3. And then my result is big R. So this is R in the x, this is R in the y. And I want to find two things. I want to find the size of the hypotenuse here, so the total distance from beginning to end. And I also want to find the angle. Okay, so that's my final steps, right? Because I drew the triangle now, and now I need to find the new resultant vector length, which is just the Pythagorean theorem. So I do square root of rx squared plus ry squared, which in this case is just going to be 6.81 squared plus 6.3 squared. 6.1 squared, 6.3 squared. So that gets to be 9.3-ish. So it's about 9.3. So I'm done with that step. And now I'm on to step 6, which is use tan inverse. So tan inverse of opposite over adjacent is what the resultant angle is. So I can just plug in my numbers here. So tan inverse of the opposite side, which is this one, opposite adjacent. So that's 6.3 divided by 6.81. And let's see what we get. Gotta remember to do this in degrees. There it goes. And so we get 42.8 degrees as our answer. Okay, so I now know the distance that we need to go to get from the start to the end, and also the angle. Why is this useful? Well, the challenge that you're going to be working on is a navigation challenge. That's the first part of it. So you're going to actually be doing this, walking and seeing, if I take this path, where do I end up? And then where does the math say that I should end up? And this is how we're going to calculate that math. And then after we kind of like really exhaust this, if it's still working okay, we can try to navigate around something. And we'll be oftentimes whenever you see vectors, you're going to want to break them into x and y components. That's basically like just find the sides of the triangles, right? So like draw a vector as a triangle, find the sides, and then you can add up all the x's together, and you can add up all the y's together, and find your new triangle, which is how you'll find your new total distance from beginning to end and total direction. Okay, hopefully that helps.